Hello students, welcome to Ask Expert. This is Sekhar from M Sigma Gokulam. As you are all aware, we have the mechanical engineering student community WhatsApp group and Telegram group, and we are into the Insta, etc. And you can reach us. You can reach us very easily into this program of Ask Expert. I would like to highlight what some of the doubts very commonly posed by the students in this mechanical engineering WhatsApp group. I want to share some of the information regarding the doubts, most commonly asked doubts from the mechanical engineering student community in our WhatsApp groups. Generally, very famously asked, very commonly asked doubt is this. See, in the thermodynamics, there are so many thermodynamic relations, equations, mathematical expressions in the thermodynamics. Which equation is suitable for what kind of process and for what kind of system? They are the commonly asked questions from the mechanical engineering graduates, because thermodynamics is a science or a branch of engineering, like or a subject of mechanical engineering, where the very many, even the experts also, even the many students also very well aware of the thermodynamics. They get confused to what equation must be picked to write a particular problem. So I would like to discuss about that particular domain of the mathematical expressions what you see in the thermodynamic subject. For example, if you just look at the most famous law of conservation of energy called as first law of thermodynamics. First law of thermodynamics itself has got three different formats for a cyclic process. That is, cyclic integral of delta W is cyclic integral of delta W, Q minus W is equal to delta U, and among all, this is the most famous equation, delta H plus delta Ke plus delta P, right? This is the also called as steady flow energy equation. This is the non-flow energy equation. Of course, this is for any thermodynamic cyclic process. Then if we just look at this conservation of energy equations, this equation is valid for any thermodynamic cycle, may be reversible or irreversible. Any thermodynamic cycle may be a reversible cycle or a irreversible cycle, or a clockwise cycle or an anti-clockwise cycle. What do you mean by clockwise or anti-clockwise cycle? Any thermodynamic cycle, if it is running in the clockwise sense, for example, Otto cycle, Diesel cycle, Breton cycle, Rankine cycle, Carnot cycle, etc., any clockwise heat engine cycle is a work producing cycle. Any clockwise thermodynamic cycle on a PV diagram or a TS diagram, it must be a heat engine cycle. It will give you the network output. That means the cyclic integral of delta W will be positive. When this is positive, this also will be positive. Okay, and valid for any thermodynamic cycle, I said. That means if the cycle is this is a work producing cycle. The cyclic integral of delta W will be positive. If you take an anti-clockwise cycle where the cyclic integral of delta W will be definitely negative, it is a work absorbing cycle. What are the work absorbing cycle? Maybe a refrigeration cycle or a heat pump cycle. They require the work. Without the work input, they can't operate, they can't transfer the heat from low temperature to the high temperature. Therefore, even whether it is a refrigeration cycle or a heat pump cycle or a heat engine cycle, maybe a reversible cycle or a irreversible cycle. All cycles are not reversible. For example, Carnot cycle is a completely reversible cycle, okay, whereas Otto cycle is not a completely reversible cycle. So, for any thermodynamic cycle, this equation is valid, okay, that's fine. That is about this particular format of the cyclic process, first law of thermodynamics. When you come to this non-flow energy equation, this is again valid for any thermodynamic process. Any thermodynamic process, whether reversible or irreversible, undergone by closed system. Whenever we talk about the closed system where there is no mass transfer between the system and the surroundings, this equation is valid, because this is a change in internal energy. Okay, so whether a process is reversible or irreversible, don't have to bother, blindly we can write. But of course, we have to follow the sign convention. When heat is supplied, positive; when heat is rejected, negative; when work is done by the system, positive; when work is done on the system, always right side final minus initial. That particular precaution must be taken. Of course, that is valid for any thermodynamic process undergone by closed system. when you come to this equation, which is called as the steady flow energy equation, again this is the sign convention where the heat supplied, this is the work done by the open system. What is steady flow energy equation? It is for a open system. Whenever there is a mass entering, mass leaving, there must be a mass entering and there must be a mass leaving. Like a turbine, compressor, pump, nozzle, throttle valve, diffuser, for all kinds of the steady flow open systems, this is valid. So, but this is also valid for any thermodynamic process, whether reversible or irreversible. Any thermodynamic process, whether reversible or irreversible, undergone by steady flow open system. This is called steady flow energy equation, undergone by steady flow open system. I can give so many examples for the steady flow open systems. Fan, blower, compressor, turbine, pump, fan, blower, turbine, compressor, pump, throttle valve, or nozzle, diffuser, all are steady flow open systems. For all those things, any thermodynamic process, whether reversible or irreversible, you are able to write that particular equation. You don't have to bother the type of the process or the nature of the process. Then actually somebody may ask, what is this reversible and irreversible? Generally, a reversible process can be thought of as a hypothetical, ideal, not practically feasible, something like a Mr. Perfect. Reversible process I can call something like a Mr. Perfect. So, which is can never be, can you see any person Mr. Perfect? Never. Like that, reversible process is also a purely an imaginary, ideal, hypothetical, theoretical process wherein all the irreversibilities are absent. When I say irreversibilities means, what will make a thermodynamic process irreversible? There are so many factors like a mechanical friction, rubbing friction, or viscosity, or a turbulence, or eddy currents, mixing, all these things, electric resistance, magnetic hysteresis. There are so many parameters that can render a thermodynamic process irreversible. Only when all these factors are absent, then only the process can be called as a reversible. When you come together the reversible, again there are two things. When you talk about the reversible word, very famous word in thermodynamics, there are two things: internally irreversible, internally reversible, and externally reversible. Internally reversible and externally reversible. There are two things again. What do you mean by internally reversible? If the process is, if the internally reversible means, what do you mean by internally reversible? If you talk about the internally reversible, if the process is undergoing in such a way that each and every state during that process is almost under quasi-static thermodynamic equilibrium. That means each and every state during the process, if the system is almost in thermodynamic equilibrium, it is deviating, but when it is proceeding from one state to the another state, it is deviating, but the deviation is minutely very small. That means the process is happening in such a way that each and every state during the process is almost in thermodynamic equilibrium, which is also called as a quasi-static, quasi-equilibrium thermodynamic process. That thing can be thought of as an internally reversible, where all the dissipative effects like mechanical friction, etc., and fluid doesn't have viscosity, there is no mechanical friction. So, when it happens like that, it is called as a internally reversible. Internally reversible means internally within the system there are no irreversibilities prevailing. The process is happening in such a way that each and every thermodynamic state is almost in thermodynamic equilibrium. After undergoing the process, you should be able to get back to the same initial state along the same path but in the reverse direction, passing through the same states. After undergoing the process, if the system can be reversed along the same path but in the reverse direction, passing through the same states as if in the forward direction. If it is a forward direction, if it is in the forward direction, it is undergoing some states. But after finishing the state, if the process can be reversed in such a way that system is undergoing through the same states as that in the forward process, without any dissipative effects, if the process is being underwent during that expansion or compression, that can be thought of as an internally reversible. What do you mean by externally reversible? If the irreversibilities are absent external to the system during the heat interaction or work interaction between the system and the surroundings, if the external irreversibilities are completely absent, that can be thought as a externally reversible. So for supposing an isothermal process is there, I am just giving an isothermal process is there as undergoing, a liquid is undergoing phase change to the vapor. A liquid is undergoing a phase change to the vapor. Temperature remains constant. Okay, now this temperature is say 30 degrees Celsius. At 30 degrees Celsius, a liquid is converting into the vapor, isothermal process. It is definitely and internally reversible. Then what is externally reversible? If the surroundings are also at 30 degrees Celsius, the heat transfer is happening. If the temperature difference between them is tending to 0, that can be thought of as externally reversible. Heat transfer through a finite temperature difference. Supposing if it is at 40 degrees Celsius, same system is undergoing from a liquid to the vapor phase change at constant temperature, it is internally reversible. But if the source temperature is at 40 degrees Celsius, it is externally irreversible. This is internally and as well as this is internally reversible. This is internally reversible because the temperature process is constant. A isothermal process is internally reversible process. I can say an isothermal process is an example for the internally reversible process. Supposing if the temperature difference is not there between the source and the working fluid, that is called as the temperature difference is not there, but you are presuming the heat transfer. You are presuming the heat transfer Q with delta T tends to 0. This is at 30, this is at 30, heat transfer is happening. So this is externally reversible. Carnot cycle is the best example for this. Each and every thermodynamic process in the Carnot cycle is both internally reversible and as well as externally reversible. So I hope you understood what is the meaning of that reversible word. Reversible process is an ideal, hypothetical or imaginary process which cannot be practically feasible. All the processes that are happening practically, all are irreversible to some extent or greater extent. Then you may ask, students may ask, when the process is not possible, why should we study about it? Then the question comes, why should we study? Because that process is not practically feasible. Why should we analyze that? Because number one, analysis of the reversible process is quite easy mathematically because we have got certain expressions to get the work, to get the heat, etc. Number one. Number two, we can make out by what extent the practical process is deviating from the reversible process, thereby try to reduce that irreversibility is in the process, thereby you can improve the efficiency of the process. If the process is lesser irreversible, I can say it is more efficient. If the thermodynamic process is carrying lesser irreversibilities like viscosity, turbulence or mechanical friction or rubbing friction, etc. There is a big list. There is a big list which may render a process irreversible. If you can reduce the irreversibility during that process, definitely the efficiency of that process will be more. So it is always advisable to first study the reversible process, which is a hypothetical or idealized process, and then compare that performance of that idealized process with the practical irreversible process, and by what extent the practical actual process is deviating from the reversible process. Try to reduce the gap so that the efficiency of the process can be improved. Say for example, Carnot cycle. Carnot cycle, why it is the most efficient heat engine? Because all the processes in the Carnot cycle are both internally reversible and as well as externally reversible, that is complete reversible. You can process, all the four processes are completely reversible in the Carnot cycle. That is true with the reversed Carnot cycle also. Carnot refrigerator and Carnot heat pump, they are having the highest COP among all the refrigerators and the heat pumps. No refrigerator can have a more COP than that of the Carnot refrigerator. Similarly, no heat pump can have a more COP than the Carnot heat pump, which is also called as the reversible heat pump. Whenever you use the word reversible, it means that that particular device may be operating to be operating on Carnot cycle. In fact, almost all the GATE papers, in fact GATE 2024 also, GATE 24, recent GATE 24 also, he has asked the cycle is operating on a reversible cycle. That means he has also asked like this, what is the maximum work you can obtain from that particular heat engine? When can you expect the maximum work output from a heat engine? Only when it is operating on the Carnot cycle or a reversible cycle. Then only you can expect the maximum work for a given heat input. Similarly, while receiving the work, because earlier I said that there are certain heat absorbing cycles like a refrigerating cycles. So, a refrigerating cycle would require a least work, for to transfer a given amount of heat from low temperature to high temperature, so that the COP will be the maximum, because COP is defined as what is the refrigeration effect divided by work input. COP is maximum means work input will be least. So, work input will be least only when the COP is maximum. That can happen only in the case of a reversed Carnot cycle refrigerator is operating. Similarly, with the same case the case with the heat pump also. So, that word reversible, irreversible distinguishing, one must have a clear idea. In fact, second law gives the idea about that. Second law very clearly gives the idea about which equation is valid for a reversible and which equation is valid for a irreversible. For example, if you just look at the cyclic integral of delta Q by T, most famous equation in second law of thermodynamics is less than or equal to 0. Why there are given a two symbols? Whenever you are seeing a two symbols, it means that the equality sign must be equal to meant for the reversible cycle, inequality sign for the irreversible cycle. So, this is famously known as Clausius inequality. This is a very famous corollary of the second law of thermodynamics, which is called as a Clausius inequality. Why two symbols? This equation is for the irreversible cycle, irreversible, clockwise or anti-clockwise, both irreversible, and this is equality sign for reversible. Reversible means clockwise work producing cycle, or anti-clockwise cycle, work absorbing cycles. In fact, among all the thermodynamic cycles, we have a big list of thermodynamic cycles. Majority are work producing cycles like Otto cycle, Diesel, Joule, Breton, Rankine, Carnot, etc., Atkinson, Stirling. All these cycles are work producing cycles. Very few are work absorbing cycles like a refrigeration cycles like vapor compression refrigeration cycle, vapor absorption refrigeration cycle, Bell-Coleman cycle. What is Bell-Coleman cycle? Air refrigeration cycle. Only the number are lesser. Work absorbing cycles are the anti-clockwise cycles. Here for anti-clockwise cycles, cyclic integral of cyclic integral of delta cube is definitely less than 0, because this is equal to the cyclic integral of delta W is less than 0. Whereas for the clockwise cycles, cyclic integral of delta Q is greater than 0, or cyclic integral of delta W is greater than 0 for the clockwise cycles, or for the heat engine cycles. This is for the refrigerating cycles, refrigerating or the heat pump cycles. Refrigerator and heat pump both mean the same, both do the same thing. The only thing is, why two names means, based upon what effect you want from the device, we got the two different names. For example, if you take the refrigerator, our focus, our objective will be to maintain the low temperature as compared to the hotter surroundings. In your house there is a refrigerator. You are maintaining a low temperature in that cold chamber with respect to the hotter surroundings, maybe 40 or 35 degrees Celsius, but inside you are maintaining around 5 degrees Celsius average temperature, or 1 degree Celsius inside your refrigerated box. But then what is heat pump? Heat pump is a device wherein your focus is on to maintain the high temperature as compared to the very cold outer ambient surroundings. Your focus is on to maintain the high temperature as compared to the very cold surroundings, that is called as a heat pump. In fact, they do the same task. Heat pump and the refrigerator, both will require the work, both will transfer the heat from low temperature to the high temperature, both will follow the Clausius statement of the second law of thermodynamics. On what principle refrigerator and the heat pump works? On the Clausius statement of the second law. not Clausius inequality. I am talking about Clausius statement of the second law of thermodynamics, because second law has got two different statements, Kelvin-Planck and Clausius. If the Kelvin-Planck statement outcome is a heat engine, Clausius statement outcome is refrigerator and heat pump. Fine. So you have got this is a very famous corollary of the second law of thermodynamics. Second law of thermodynamics. Second law also gives in a different way that equations. Look at this. From second law, we can also say, from second law of thermodynamics, that I am talking about reverse, which equation is valid for reversible and which equation is valid for irreversible, or which equation is valid for any process, like that. According to the second law of thermodynamics, say for example, ds is equal to delta q reversible by T. That means delta q is equal to TdS, it is valid only for the reversible process. Only for reversible process. Supposing if the process is irreversible, this sign will become greater than. For any thermodynamic process, if you want to write, ds will be greater than or equal to delta q by T. Greater than or equal to delta for any thermodynamic process. Greater than sign for irreversible for any thermodynamic process. If delta q is positive, ds will be positive. If delta q is 0, ds will be 0 only if it is a reversible R is there. That means, if you just look at this equation carefully, if delta q is positive, that means you are supplying heat, then ds will be positive. If delta q is positive, ds will be positive. That means, I am talking about reversible process. That means when heat is supplied, entropy will increase. When delta q is negative, that means when you are taking off the heat from the system, ds will be negative. That means entropy of the system will decrease. You don't supply, you don't give the heat. This is 0. This is 0. This will be 0. But provided this is 0, this will be 0 only when the process is reversible. Got it? This is 0. This is also will be 0. That means entropy would be constant without any heat transfer, provided the process should be reversible or sign for the reversible. Supposing if the process is irreversible. If the process is irreversible, but you are not supplying any heat, you are not taking out any heat, delta q is 0, but the process is irreversible. When delta q is 0 and the process is irreversible, obviously when two signs are given, one sign, equality sign, always for the reversible, the other sign, greater than or less than, that will be for the irreversible. If there is a process is irreversible, delta q is 0, that means it is adiabatic. When you call the process as adiabatic, when the heat transfer is 0. So this is 0, adiabatic, but ds is greater than 0 because the process is irreversible. Then it is called as an irreversible adiabatic process where the entropy of the system is increasing. Supposing if it is an adiabatic process and also the reversible, adiabatic process, delta q is 0 and also the reversible, ds will be 0, that is S is constant, that process only is called as a isoentropic. Iso means constant entropy, same entropy, entropy will not change. That means this is for any thermodynamics. This is for the irreversible, this is for the reversible, this is for the reversible. That means delta q is 0 and the process is reversible, then only S will be constant. This is only, it is called as isoentropic. Try to understand that. Only isoentropic processes only can be thought of as a vertical process, like this isoentropic compression, this is isoentropic expansion, this is isoentropic expansion, this is isoentropic compression. Very famous processes when you study in the gas turbine cycles and steam turbines. This is an isoentropic pumping or isoentropic compression. These are pressure lines. These are pressure lines. These are isoentropic expansion. These lines are the constant pressure lines. Okay. So any such kind of a vertical process, this is a isoentropic process. For that process only this equation is valid. If this is 1, this is 2, P2 by P1 whole power gamma minus 1 by gamma is equal to T2 by T1. This is strictly a reversible adiabatic equation or isoentropic. Strictly, very strictly. You should never write for the irreversible adiabatic. Most of the thermodynamic problems people will slip that this equation it is strictly a isoentropic equation. Never write for the irreversible adiabatic where the entropy of the system is increasing. Supposing if the process is proceeding like that, if the process is this white color one, no, can you write between this state and this state this equation? Never, should not write. We can only write for this yellow color lines, this one, this equation. Okay, when it is going right, see that in both the cases it is going only right. That means this is adiabatic, this is adiabatic, this is also adiabatic, this is also adiabatic, this is also adiabatic, but this is irreversible adiabatic, this is reversible adiabatic. This is adiabatic with friction, this is adiabatic without friction. Adiabatic process without friction can be called as a reversible process. Reversible adiabatic process also called as isoentropic process. Isoentropic means a process should be a reversible, that is frictionless adiabatic. Okay, the white color one, it is at the entropy in the white color one, entropy is increasing. We can see that entropy is increasing for the white color one. See why it is there, the entropy is increasing? Because of the internal irreversibilities during the adiabatic process, entropy gets generated. Entropy is such a thermodynamic property that it is always getting created. Once created, it cannot be destroyed. If you just look at the entropy and energy, two very important terms in thermodynamics. After all, thermodynamics is the subject of three E's: equilibrium, energy and entropy. Zeroth law for the equilibrium, first law for the energy, second law for the entropy. When you just look at these two E's, three E's there, equilibrium, energy and entropy, out of which the second two E's, if you take energy and entropy, energy is different from the first law and entropy is different from the second law. Just compare these two things, energy is very easy to understand. You can understand the energy very easily because we have been talking about the energy since 8th class, potential energy, kinetic energy, etc., etc. But in thermodynamically speaking, internal energy is the sum of all the molecular forms of energies, potential, kinetic, rotational, vibrational, etc. But when you come to the entropy, what is after all entropy? Entropy is a thermodynamic process which something talks about the irreversible nature of the process. See, the reversible, I am just these doubts, all these doubts which I am pertaining to the reversible or irreversible I am discussing now in this ask your expert. See that in the entropy is that property which something very closely linked to the reversible nature or irreversible nature of a process. We just look at this. Entropy remains constant if it is reversible adiabatic and entropy is increasing. And entropy is increasing during the irreversible adiabatic process. This is the entropy gets generated during the irreversible adiabatic process. Energy will never be created. You can never create an energy. You can only convert from one form to the another. Electrical energy to the thermal energy, or mechanical energy to the thermal energy, or thermal energy to the mechanical, like that. Energy is always conserved according to the first law, but entropy is never conserved. Entropy is never conserved. Once created, it can't be destroyed. It keeps getting generated. Entropy keeps getting generated during every irreversible process undergone by a system. If there is an irreversibility during a process, we can suspect that yes, there is an entropy generation in the universe. When I talk about universe, I have to take both system and I have to take both the surroundings. Suppose that a thermodynamic process is undergoing an irreversible process. Some heat transfer is there, irreversible. Definitely I know that it is irreversible. This is delta S of the system will decrease because it is losing heat, but delta S of the surroundings will increase because surroundings are gaining heat. But because the process is irreversible, the net change in the entropy of the thermodynamic universe should be greater than 0. That is what should be very famous equation of the second law. Delta S of the thermodynamic universe, which is the sum of the delta S of the system plus delta S of the surroundings. If we just add up, if that net sum will be greater than or equal to 0. This greater than sign is valid for the irreversible and equality sign for the reversible. Whenever any two such symbols are there jointly given, greater than or equal, less than or equal, generally considered that equality sign for the reversible, and other sign, greater than or less than, like in a Clashes inequality, just shown you the Clashes inequality there. It just shown you the Clashes. So this is for the irreversible cycle, this is for the reversible. This is for the cycle, valid for both clockwise and anti-clockwise, both clockwise and anti-clockwise. And coming here, and this sum, delta S of the system plus delta S of the surroundings, if it is greater than 0, the process will be irreversible. If it is less than, if it is equal to 0, say for example, if it is equal to 0, the process would be reversible. The process, supposing, if it is it possible, delta S of the thermodynamic universe is less than 0, such process will never be possible. Never possible. It will violate the second law of thermodynamics. Entropy of the system may increase or decrease. Entropy of the surroundings may increase or decrease. But the total sum, the net change in the entropy of the universe, which is a sum of the entropy change of the system plus entropy change of the surroundings, we just add up algebraically, that will never be less than 0. If it is less than 0, that process will be violating the second law of thermodynamics. According to the second law of thermodynamics, the entropy of the thermodynamic universe always tends to be a maximum. It keeps increasing. So at this instant, if there is some entropy in the universe, and after next second, the entropy of the universe will definitely be more than that, what is the value existing now. It keeps increasing. It keeps increasing. It is going uphill. It is going upper. It is climbing an uphill of the entropy. The entropy of the universe will never be decreasing. If it is remaining constant, all is well. The process is reversible. There are no losses. There are no, everything is reversible. No, a process is it has got limit. It has got a limit. It would just become the reversible. So at that instant, the entropy of the universe, the process must proceed in such a way that the limiting value of the change in entropy of the universe should be equal to the 0. Limiting value, that is, that entropy change of the universe is less than 0, that means that process would never be possible. It can never happen. On that, there are so many questions being asked in the gate. For example, if there is a flow happening, it is an adiabatic process. Say for example, it is an adiabatic, no heat transfer. We know that from adiabatic process, in an adiabatic process, entropy change of the system will always be positive or equal to 0. Because if it is an adiabatic, what is the delta S of the surroundings? Delta S of the surroundings is 0 because there is no heat transfer because the process is adiabatic, no heat interaction. That is, the change in entropy of this system, this is the system, should be either greater than 0 or equal to 0. Why two symbols? This is for reversible, this is for irreversible. Now, if we just take this as one station, this is a second station. If the flow is happening from 1 to 2, in such case, S2 will be definitely greater than S1 or equal to S1. It can never be less than, S2 will never be less than S1. Either it should be greater than S1 or equal to S. If it is equal to S1, fine, well and good, the process will be reversible adiabatic. If it is greater than S1, S2 is greater than S1, which means that it is an irreversible adiabatic with friction, but S2 can never be less. If it is less than S1, it will simply violate the second law of thermodynamics. So that is called as a reversibility and irreversibility during a process. If the process is irreversible, there are inherent losses that are involved during the process. So that if the process is irreversible, that would finally result in the net change in entropy of the universe is greater than 0. Entropy of the universe can never decrease. Either it remains constant if the process is reversible, it would increase if the process is irreversible. If the entropy of the universe is decreasing during a process, means that process can never exist, because that will simply violate the second law of thermodynamics. So that is how we could understand the irreversibility and irreversibility of a process via entropy, because entropy is an outcome of the second law of thermodynamics. Entropy change during a process could measure the irreversibility involved during that process. If the process is involving more and more irreversibilities, that particular process would be generating more and more entropy in the thermodynamic universe. I can say that the entropy generated during a thermodynamic process, the entropy change of the universe, the entropy generated during a thermodynamic process for a thermodynamic universe will indicate how much irreversible that process would be. If there is a greater entropy generated during a thermodynamic process in the universe, a process is undergoing, it is generating more entropy in the universe. I am talking about universe. Please note that I am talking about universe. Change in entropy of the universe means change in entropy of the system plus change in entropy of the surroundings. Supposing if during a process, thermodynamic process, if there is a more entropy generated in the universe, there is a more change in entropy of the universe, such process would be called as a more irreversible. Supposing there are two processes, there are two heat transfer. Best example for the irreversible process is heat transfer through a finite temperature difference. T1 is greater than T2. This is the best example to understand the irreversible. A heat transfer occurring through any finite temperature difference is irreversible. Any heat transfer that happens with no temperature difference, as you imagine in case of the Carnot cycle. Carnot proposed. Nicolas Sadi Carnot, a pioneer in the thermodynamics, is a French military engineer. He has he has conceived a thermodynamic cycle in such a way that in his heat engine he transferred a heat without any temperature difference. How can it be possible? Can you transfer the heat without any temperature difference? Yes, even if you propose that, it would take infinite amount of time. Supposing if you want to transfer heat from a body at 100 degrees Celsius to a body at 100 degrees Celsius, two bodies are there, one is at 100, other is also at 100. You are proposing a heat transfer, say 1 joule of heat, just 1 joule of heat. For that 1 joule of heat, if it takes around 5 years, imagine that. You can't wait for that 5 years time. If that 1 joule of heat transferred from 100 to 100, if you think of that would be happening for 5 years, yes, it would happen. Then that can be thought of as a reversible heat transfer. That is why Carnot cycle has the two exactly opposite kind of processes. One is reversible isothermal and other is reversible adiabatic. Reversible adiabatic is super fast, deadly, terribly fast, and reversible isothermal process is super slow, deadly slow. So you have arranged two kinds of the processes alternatively, isothermal adiabatic. In his Carnot proposed a cycle in which we have a reversible isothermal process which is very slow, which is internally reversible and as well as externally reversible, and followed by a reversible adiabatic process which is also reversible but without any heat transfer, which must proceed very fast. Why it should proceed very fast? There should not be any time available for the heat transfer. Any process that happens so rapidly, super fast, can be thought of as an adiabatic. A bomb explodes, yes, it is an adiabatic, because no time it will explode. A tire punctures, a high pressure tire punctures, yes, you can thought of as an adiabatic, because process is finished in no time. That can be thought of as an adiabatic. It may be reversible or irreversible, I am not talking. I am just talking what is the meaning of adiabatic? Adiabatic means super fast process can be thought of as an adiabatic. You are listening my voice, supposing you are sitting somewhere around the far, you are listening my voice, that can be thought of as an adiabatic. Of course, it is reversible also. That is why the velocity of the sound wave, is calculated assuming that the propagation of the sound wave is under reversible and adiabatic conditions. That is why the most famous equation to calculate the velocity of the sound is given by this. Velocity of the sound is calculated as square root of dou p by dou rho at constant S. The suffix means it is a constant, isoentropic. Sound wave, the velocity of the small pressure disturbance created at a particular point in a medium, fluid medium, is assumed to be propagating under adiabatic and as well as reversible conditions. Please note, that's very important point this is. velocity of the sound wave, which we call it as a 330 meters per second. No, in the physics also you learned that 330 meters per sound wave propagates at 330 meters per second in a room. So how did you calculate that? By using this, simply that by this equation is used gamma RT, thus is 330 meters per second. The velocity of the sound in a air at room conditions, gamma of air is 1.4, R of air is 287, temperature of the room air is around 25 plus 273, you get 330. That means you are assuming that process is reversible and adiabatic without generating any entropy. So because sound wave propagates very fast, that is why any fast process, I mean to say that any rapid super fast process can be thought of, can be imagined as an adiabatic process, because there is no time available for the heat transfer. After all, adiabatic means no heat transfer, Q is 0. So adiabatic process, it should not have any heat transfer, further don't allow any time. Contrary to that, reversible isothermal process must proceed very slowly, infinite slowness. And Carnot has arranged two processes, reversible isothermal, reversible adiabatic, reversible isothermal, reversible adiabatic. How can you assume that kind of how can you justify, how can you practically achieve that cycle practically? Because this is proceeding very slow and very fast, very slow, very fast. A cycle is operating. This is the Carnot. This is the Carnot having the highest thermal efficiency. All four processes are both internally reversible and as well as externally reversible. Because Carnot has proposed a heat transfer, with delta T tends to 0. And Carnot proposed a heat rejection with delta T tends to 0, which will never happen. That is why Carnot engine has got the highest thermal efficiency among all the heat engines. Highest thermal, because all the four processes are reversible internally and as well as externally. It has got highest thermal efficiency among all the heat engines. No heat engine can have a thermal efficiency more than that of Carnot. If it has, if any engine has, it will simply violate the second law of thermodynamics. But is it possible? Never possible. It is there in its name also. Not possible, you can say. The cycle can never be possible to achieve. But why should we study that? I already said. Why should we study that? Means any heat engine, practical heat engine cycle is compared with the Carnot, how much deviation we have, the practical cycle from the Carnot, and try to reduce the deviation, try to approach the Carnot cycle, and automatically that practical heat engine also efficiency also will increase. So the idea of studying that hypothetical or ideal most processes called as reversible processes or cycles called as a reversible cycle like a Carnot cycle. The idea is by eliminating the irreversibilities during the process or during the cycle. After all, cycle and process is the only different that a process is initial and final states are same or different. For a thermodynamic process, initial and final state are different. For a cycle, the initial and final states are same, because after undergoing two or three or four processes, you are reaching to the same initial state. So if you are able to eliminate the irreversibilities prevailing during the process or during the cycle, the efficiency of that particular thermodynamic cycle or the process can be increased. So that is why we have to study that reversible processes, reversible cycles. Theoretically we have to study, even though they cannot be practically implemented. Carnot cycle cannot be implemented, but we have to study that. What is happening in the Carnot? Try to approach that. That is what we do in the Rankine cycle. So in the Rankine cycle, we provide the regeneration. In the Rankine cycle, you are providing the regeneration. What is the advantage of providing the regeneration? It will improve the efficiency of the Rankine cycle. How it will improve? Because by providing the regeneration in the Rankine cycle, we are trying to reduce the gap between the Rankine cycle and the Carnot cycle. Thereby, the efficiency of the Rankine cycle also can be improved. Yes, regeneration results in the improvement of thermal efficiency of the Rankine cycle, because the mean temperature of heat addition will increase. See, Carnot cycle efficiency is this 1 minus TL by TH. Any method you adopt, if you increase the TH, efficiency will increase. That is what we do by providing the regeneration in the Rankine cycle, regeneration in the Breton cycle. Regeneration in any cycle, why that thermal efficiency of that particular cycle will increase? You provide regeneration in the Rankine cycle. Result is efficiency is increased. You provide the regeneration in the Breton cycle, regenerative Breton cycle. That also improves the efficiency. So, why the efficiencies of Rankine cycle and Breton cycle are improved by providing the regeneration? Because you are trying to reduce the gap of what? Your gap in terms of the irreversibilities. You are trying to reduce the gap of irreversibilities between the Carnot and those cycles, thereby the efficiency of those cycles is increased. By providing regeneration, this mean temperature of heat addition is increased in the Rankine cycle. That is why this is the original Carnot cycle formula. If this is improving, this will increase. That means that will happen in the practical Rankine cycle also. By increasing the mean temperature of heat addition, we are trying to reduce the irreversibilities in the Rankine cycle. Thereby your efficiency of the Rankine cycle is also increased. Okay. So, I hope you got the clear some idea about what is the difference between the reversible and irreversible there. Okay. Because reversible is hypothetical, ideal, not practically feasible. All practicals are to some extent or greater extent irreversible, thereby they are generating some entropy in the universe, because there is some irreversibility during a process, there is some entropy generated in the universe. If it generates more entropy in the universe, it is a more irreversible. If it generates lesser entropy in the universe, it is lesser irreversible. So, the degree of irreversibility, how much irreversibility is there during a process, we have a measure for that. What is that measure? Calculate the entropy change of the universe during that process. Supposing two processes are there, both are irreversible. Which is more irreversible? How do you check? Calculate the entropy change of the universe in this, calculate the entropy change of the universe in this. Which is generating more entropy in the universe, you tick that as thermodynamically more irreversible. Okay. So, that is how we can have the comparison between the reversibility and irreversibility of a process. And remember this formula, this is in fact this in the compressible fluid flow, this velocity of sound or the acoustic velocity plays a very significant role. In the off late they are asking many questions, because that velocity of the sound is given as velocity of the fluid divided by acoustic velocity. This is very famously known as Mach number, defined as square root of inertia force by elastic force or compressibility force, both mean the same. This is the definition for the Mach number, velocity of the fluid divided by velocity of the sound in the fluid at local conditions. That ratio is called as the Mach number. This velocity of the sound is in the air only, you can in air it can be calculated by using a gamma. In fact, velocity of sound is a thermodynamic property. Gamma is adiabatic index. This is a thermodynamic property. We can think of velocity of sound in an ideal gas as its thermodynamic property, because T is a property, R is a property, gamma is an adiabatic index, Cp by Cv. This if it is m is greater than 1, it is supersonic, m is less than 1, subsonic. This is supersonic, this is subsonic. When you talk about supersonic and subsonic, I will try, one thing is striking in my mind to teach you, that is called as a shock wave. A normal shock, again shock waves are two types, normal shock and oblique shock. What is the shock wave? When does it happen? A shock wave could happen during the flow of a compressible fluid in a supersonic nozzles. A shock wave could happen inside a varying area duct, maybe a supersonic nozzle. A supersonic nozzle is maybe defined. In this diverging portion, there is a shock wave could happen. A shock wave is an abrupt, very sudden deceleration of the fluid from supersonic flow to the subsonic flow. This is called as a normal shock. A one-dimensional normal shock. A one-dimensional normal shock you may see in the diverging portion of a supersonic nozzle. Once the shock wave happens, the fluid after the shock, if the flow is like this, the fluid after the shock should have to be subsonic. Before the shock, it should be supersonic. A shock wave is an abrupt deceleration or the reduction in velocity of the flowing fluid. Whenever a supersonic flow abruptly decelerates into the subsonic flow, particularly in the supersonic nozzles and of course also in the supersonic diffusers. Mach number must change from m is greater than 1 to the m is less than 1. If the flow is not greater than 1, that shock would never happen. You can never think of a shock wave. You will not see any shock wave if the flow is initially is not supersonic. After the shock wave, the flow must be decelerated to the subsonic. Therefore, during which the pressure, because the fluid has clearly decelerated, that must result in the increase of pressure, because when the velocity is decreasing but pressure is increasing, because dP by rho, from the Euler's equation, dP by rho plus VdV is equal to 0. If you just take, of course, that is when dP is dV is negative, means dP should be positive. So pressure will increase, static pressure will increase, but stagnation pressure will decrease. Static pressure will increase, stagnation temperature remains constant. Across the shock wave, T naught remains constant, but stagnation pressure decrease. Static pressure will increase, velocity decrease, Mach number decrease, all these things will happen. Stagnation temperature remains constant. So these are the things. Density will increase, pressure will increase, temperature also will increase, but stagnation temperature, remember that these are the stagnant T naught, total temperature or the stagnation temperature. Total quantities are indicated as stagnation quantities. T naught remains constant, but stagnation pressure will decrease. Because I got the, I thought of as the, the velocity of the sound wave was started. Velocity of the sound wave is the velocity of a small pressure disturbance created in a medium. At what velocity it is propagating through a fluid medium. It is called as the velocity of the sound. The ratio between the velocity of the fluid divided by the velocity of the sound in the fluid is called as a Mach number. If the supersonic flow abruptly decelerates to the supersonic flow, means Mach number greater than 1. You can see such flows only in the convergent divergent nozzles at the end of a rocket. You will see a supersonic velocities of the fluid in the rocket engines, jet propulsion engines, turbojet engines, in the turbojet engines, rocket engines, above all D-level nozzle, D-level steam nozzle, D-level turbine you must have heard, which is a pure impulse steam turbine. D-level nozzle is a supersonic steam nozzle where the velocity of the steam may be around 600-700 meters per second. It impinges on the pure impulse turbine. It is an impulse turbine, steam turbine blades. D-level nozzle is the best example for the supersonic nozzle. In such supersonic nozzles only, that too in the diverging portion. It will never happen in the converging. You will never see the shock in the converging or at the throat. You will see only in the diverging portion, because there only the velocities may reach the supersonic velocities and abruptly it may decelerate to the subsonic. Why it happens? You may think that why it is happening. First of all, means you are not maintaining a proper back pressure. If the design back pressure is not maintained, that means even the supersonic nozzle is operating under half design conditions. When the proper back pressure is not maintained, there is a very likely chances that a supersonic flow abruptly decelerates to the subsonic flow, where all these the changes in thermodynamic properties will happen. Stagnation temperature constant, stagnation pressure decrease, static pressure increase, static temperature increase. Then how about the entropy? Because we are finally moving around that entropy, a second law of thermodynamics property. Entropy greatly increases. Not increase, greatly, because lot of irreversibilities are there. It is an adiabatic, no doubt it is adiabatic. Any nozzle is by default adiabatic, any diffuser is by default adiabatic. Any nozzle, any diffuser by default you consider as adiabatic. Friction will be there or may not be there. If friction is not there, well and good, it is an isoentropy. But when shock is there, it means that there is a lot of irreversibilities across the shock, during which entropy definitely increase. A shock wave is an abrupt deceleration of a supersonic fluid into the subsonic fluid, during which a lot of internal irreversibilities, vibrations, etc. will happen across the shock wave, resulting in the increase in entropy of the system. Because in adiabatic, lot of irreversibilities are there, entropy greatly must increase. That change in entropy should be positive. Temperature increase. So, these are the changes you see in that shock wave. Energy, that means during every irreversible process, like in the case across the shock, the available energy of the fluid gets reduced. The available energy of that flowing fluid got reduced. After the shock wave, the available energy of the fluid got reduced greatly because of that internal irreversibility is prevailing during that shock wave. In fact, this was a question asked in gate 24 also. Across the shock wave, what will happen? In fact, in gate syllabus of 24, this question was asked. In fact, the compressible fluid flow questions are coming very often in the recent gate. Gate 23 was asked, 22 also was asked. So, because analysis, if you want to analyze the compressible fluid flow, the very first thing what you have to notice is velocity of the sound wave, you have to understand, and also the Mach number, and how the Mach number changes, how the pressure and velocity and area. There are three things that will change: area changes, pressure changes, area changes, pressure changes, velocity changes, temperature changes, density changes. All these parameters are changing. See, here dI is negative. Okay, then the dV may be negative or positive depending upon this equation. dV by dA by A is equal to dV by V into m square minus 1. This is the governing equation for the compressible fluid. dA by A is dV by V into m square minus 1, where m is the Mach number of the flow. So, based on which, supposing if dA is negative, if the flow is subsonic means m is less than 1. This will be negative. When this is negative, therefore dV must be positive. Minus and minus, that means dV is positive. This will be acting as a nozzle. When the velocity is increasing, the flow will be, such device will be called as a nozzle. If the velocity is decreasing in the direction of the flow, it is called as a diffuser. Nozzle and diffuser, just opposite actions. So, I hope you understood the conditions, mathematically how do you express the equations regarding regarding reversible or irreversible. Some equations are valid only for the reversible, some equations are valid only for the irreversible, some equations are valid for any. For example, this is there, very famous TdS Gibbs equation. TdS is equal to du plus pdv. TdS is equal to dH minus pdp. These are TdS Gibbs relations, Gibbs equations. They are valid for any thermodynamic process. Valid for any thermodynamic. Why? Why like that? Why any thermodynamic process, whether reversible or irreversible, undergone by a pure substance? Any pure substance. You can write for steam, you can write for air, you can write for refrigerant. Any process, reversible or irreversible. The reason is, all five are thermodynamic properties. Temperature, entropy, internal energy, pressure, specific volume, all are thermodynamic properties. Any property relation, any thermodynamic property relation is independent of the path. That can be integrated between any two states. Any thermodynamic property relation is independent of the path. You can integrate along this, you can integrate along this. So, irreversible of the path. So, if you just take P1 minus P2 is same for path A and same for path B. We do not have to bother what path it is. The change of pressure is same, the change of pressure between 1 and 2 is same for this path and for this path. That is why properties are called as a point functions. Inexact, point functions are exact differentials, all the properties are exact differentials, pressure, volume, temperature. So, these are the relations among the five properties which are independent of the path. Therefore, reversible or irreversible do not have to bother. Here also, temperature, entropy, enthalpy, specific volume, pressure, they are called as the TdS relations, Gibbs relations. You can write for any substance, any process. Okay. So, Certain relations are valid for any process like this. Certain relations are valid only for the reversible. For example, delta W is equal to PdV. Only for reversible. Only for reversible. Delta Q is equal to TdS. Only for reversible. Only for reversible. Okay, you can't write for irreversible. And again, for only for ideal gas, again there are certain relations. Cp into dt, du is Cv into dt. Only for ideal gas. These are exclusively reserved for the ideal gas, like air. Pv is equal to mRT, which obeys Pv is equal to mRT. Whereas they are valid for any pure substance. Any pure substance. You can write for steam. You can write for the refrigerant. You can write for the air. All are pure substances. You can write for the steam. You can write for the refrigerant. You can write for the air also. But these are exclusively for the ideal gas like atmospheric air. Okay. So, in this Ask Expert video, I hope you understood the very commonly asked doubts that reversible, irreversible, which equation is valid for what. I hope I was able to clear some of the very most commonly asked doubts about the reversible, irreversible equations that are used in the thermodynamics. And keep logging into that link. If you have got then Ask Expert WhatsApp group is there. You may post your questions there. You will be ready with the answers. Good luck students. All the best. This is Sekhar from M Sigma Gokulam.